Right. So the next set of talks would be merged talks. So the first one would be, so like we have two talks. So the first one is moderate deviation analysis for quantum state transfer. This will be presented by Navneeth Ramakrishnan on behalf of himself and his collaborators. And the second talk will be optimal change point detection with training sequences in the large and moderate deviation regimes. Will be presented by Haiyun on behalf of himself and collaborators. So I would request Navneeth Ramakrishnan to, all right, fine, he's already there. So please share your screen and the floor is yours.
Sorry, I'm trying to get it to share my screen. It says I don't have permission to share content. Is there something? Sorry, Tanmay, it says I don't have permission to share content.
Just give me a second. Can you just try once again? Like, has it started to work for you?
No, it still says it's, so the only options I have are blocked and always blocked. Somehow the allow option.
I mean, do you have the ability to share your whole screen instead of specific content?
No, I am trying to share my whole screen. Actually, I'm trying both, but neither work. I'm saying entire screen now, but yeah, it still says we can't. Yeah, that I don't have permission to do it.
Okay, so how about this? We perhaps ask Haiyun to go first, and then we'll, I mean, if possible, and then we'll see like about yours. Is that fine?
That sounds good. Thanks.
All right, Haiyun, could I please ask you to share your screen and start your presentation?
Okay, let me try. Am I sharing my screen now?
I mean, I can see something. I mean, I think I can see. Yes, I think I can see.
Can see? Okay.
Yes. Okay. Please carry on.
Okay. Hello, everyone. Today I'm going to present a paper that is called "Optimal Change Point Detection with Training Sequences in the Large and Moderate Genes." So it is a joint work by me, Dr. Zhang Qiaosheng, and Prof. Vincent. We are from the National University of Singapore. So in this paper, we consider the change point detection problem with training sequences. Let's give an example about room light change detection. For example, if you want to use a sensor to detect when the room light changes from on to off, and we are given a test sequence of sensor data that have been collected in this room previously, and there exists a change point in this sequence. So we call this kind of problem as offline change point detection problem. Since we don't know the underlying detection, underlying distributions of the sensor data in this environment, we can only collect another two sequences of sensor data when the under the situation when the light is on or off, respectively. So we call these two extra sequence as training sequences. So we can make use of this kind of training sequences to design an estimator in this sensor to find out where is the change point in the previously provided test sequence of sensor data. And in this paper, we mainly derive an asymptotically optimal estimator based on the training sequences under both the large and moderate deviations regimes. In large deviations regimes, we require the undetected error probability decays exponentially fast, and in the moderate deviation regimes, it decays sub-exponentially fast. And we also derive an asymptotically optimal confidence between the estimated and true change points under both regimes. We define the confidence width as half of the confidence interval around the change point C. So the red region is the confidence interval, and delta is the confidence width. And we also study the dependence of the optimal confidence width on various parameters. So let's go to the problem setup. Assume that we have a sequence of observations x1 to xn, and this is also called the test sequence we want to detect. And we assume that there exists a single change point C in this sequence. So before the change point C, we assume that the sensor, the observations are ID from the distribution P1. And we also assume that we have another sequence of training data denoted by Y11 to Y1n, and they are all ID from P1. Similarly, after the change point C, we assume that the sensor, the sequence is ID from P2, and also we have another training sequence Y2n that are also ID from P2. And P1 and P2 are not equal, and we assume that their scores are also equal to the size of the alphabet. Furthermore, we assume that the length of the training sequence is denoted by n and is equal to Rn. So the ratio, so R represents the ratio between the length of the training and test sequence. We want to design an estimator that can either output one of the n points in the test sequence to be the change point, or declare an erasure event if we are not confident enough to declare any of the endpoints in the test sequence to be the change point. And we consider the following performance metrics. Given any change point C, we define the undetected error probability as the probability when the estimator outputs a point that does not belong to the confidence interval around the true change point C, and also it does not output the erasure event. So delta is defined as the confidence width between the estimated and true change point. And we define the erasure probability as the probability when the estimator outputs the erasure event. Sorry. So we say that an estimator is good enough if the worst case erasure probability is upper bounded by a constant value epsilon, and the worst case undetected error probability is upper bounded by some exponential term. So lambda denotes the error decaying rate. When t here is equal to 0, then it means this term decays exponentially fast, so it is the large deviations regime. When t is in between 0 and half, then we say that it's in the moderate deviations regime because it decays sub-exponentially fast. Our goal is to design an estimator that is good enough and satisfy these two conditions. And by fixing all other parameters, we're interested in finding out what is the smallest achievable delta, that is the confidence width in this problem. We define the optimal normalized confidence width as follows. So recall that delta n is the confidence width. So this term is called the normalized confidence width. And we say that delta bar that satisfies this condition is the achievable normalized confidence width. So the optimal normalized confidence width delta bar star is defined as the infimum of over all achievable delta bar. And note that if the if delta n, the confidence width, is greater than n over 2, then this will be a trivial case because we can easily design some estimator that always outputs n over 2, and there will be no error and no erasure. So the probabilities are all equal to 0. So we only consider the case when delta n is smaller than n over 2. In the main results, we make use of the following important information quantities. The first is generalized Jensen-Shannon divergence, which is a linear combination between the KL divergences of the two distributions. And we similarly define the L divergence, which is a linear combination of the GGS divergences, and it measures the tuple of 4 distributions, the distance between the 4 distributions. So based on the definition of GGS divergence, we define the function G1 and G2 by fixing any alpha for beta smaller than alpha. We say that this G1 function corresponds to the blue line in this figure, and this is a decreasing function of beta, and G2 corresponds to this red line, which is an increasing function of beta. So we see that when beta is equal to alpha, G1 and G2 are both equal to 0. So there exists a point iota alpha such that the value of G1 when beta is equal to iota minus delta bar is equal to the value of G2 when beta is equal to iota plus delta bar. So, and this is the value of the G1 and G2. So for different value of alpha, we have different iota alpha and different value of G1 and G2. And we define the G mean as the minimum value over all possible G1 and G2 and multiplied by the ratio R. So G mean is an increasing function of delta bar. So the inverse of G mean exists, and is also a strictly increasing function. Then we come to the main theorem. In the large deviations regime, the optimal normalized confidence width is equal to the inverse of G mean function for any lambda in between this interval. Otherwise, the optimal normalized confidence width will be 1 over 2, which is a trivial case we have discussed before. In the moderate deviations regimes, for any lambda greater than 0, delta bar star is given by this expression, which is dependent on the chi-square distance between P1 and P2, and also dependent on the error decaying rate lambda and the length ratio R. Later, we'll explain how the parameters, how this delta bar star depend on different parameters. So in this result, we can see that delta bar star is independent of epsilon. That is the upper bound for the erasure probability. So strong converses hold for these results. In the achievability proof, we make use of the following estimator, and which is asymptotically optimal. So define any row within 0 and R. Recall that we have the test sequence xn and y1 and the training sequence y1n and y2n. Now we truncate these 3 sequences to construct another 4 new sequences. So for any j in between 1 and n, we truncate the test sequence into 2 parts. And then for any row n, we truncate the training sequence into 2 parts, one with length row n, and the rest, and similarly for the other training sequence. So we combine the row n length training sequence with the first part of the test sequence and let it to be x1 tilde, and similarly we construct another sequence x tilde 2. So now we have 4 new sequences, and then we calculate the types of these 4 new sequences. So we denote the new tuple of types as tj row. So we make use of this type to construct a test statistics SI. SI is the minimization over the L divergence of the tuple of types LTJ row. So the bigger the SI is, it means that the divergences between the tuple of types are bigger. So the estimator outputs an erasure event if all Si are smaller than lambda. Otherwise, if there exists an I such that Si is greater than lambda, we output this index I to be the estimated change point. If Si greater than lambda, it means that yeah.
Hello. So we also have a second speaker for this talk. Can you like finish off within the next 1-2 minutes?
Yeah, I'm going to finish it soon. Yeah, right. So yeah, so we also prove that when rho is approximately equal to the n to the power -1/4 is asymptotically optimal. So yeah, in these two figures, we can see that the delta is an increasing function as lambda, that is the error decaying rate, and also a decreasing function of r, that is the ratio between the lengths, the training and test sequence, and also it's a decreasing function of the distance between the P1 and P2. So in this paper, we mainly derive the asymptotically optimal normalized confidence width and also an type-based estimator. So the possible future extension is to extend it to the online change point detection problem. Yeah, thank you very much.
Thank you. So
I can stop sharing now, right?
Okay, I think you should be able to see my screen now.
I still don't see anything. I can see, viewing Navneeth Ramakrishnan's screen, but I don't see anything as such.
Oh, do you see anything now, or?
No, I don't see anything.
Weird.
Oh, I saw it.
Oh, okay. So can people see the slides right now?
Yeah.
Okay, great. Yeah, sorry about those issues. I'm going to be, let's start. So I'm going to be talking about moderate deviation analysis for quantum state transfers. This is work done jointly with Marco Tomamichel and Mario Berta. So here's a quick outline of my talk. So I'm going to be starting with quantum state splitting and explaining what the information processing task there is. And then we'll move on to the cost of quantum state splitting in terms of a quantity known as the partially smoothed max information. And then we will look at this in the moderate deviation regime, where we have an expansion for the partially smoothed max information for IID states. And then finally, we will end with some open questions. So before we go into the talk itself, let me introduce the information theoretic quantities that you will encounter. So we have the von Neumann entropy and the relative entropy, which I guess most people are familiar with. We also have the relative entropy variance, which will show up in some of our results, and that's defined as shown here. We have the max relative entropy between rho and sigma, which is defined as the smallest lambda, where 2 to the lambda sigma is larger than rho in a positive semi-definite sense. And the min relative entropy, which is minus log of the square of the fidelity between rho and sigma. And finally, for some bipartite state rho AB, you have the max information, which is a minimization over the max relative entropy between rho AB and rho A tensor sigma B, and the minimizations over all sigma B. Next, we introduce the epsilon ball around rho. So this is the set of states which are epsilon close in purified distance to rho, where the purified distance is just the square root of 1 minus the square of the fidelity between rho and sigma. And we use this notation to denote epsilon closeness. And with this in mind, we can define smoothed versions of the quantities on the previous slide. So we have the smoothed max relative entropy, where we minimize over all the rho bars in the epsilon ball around rho. And similarly, the smoothed min relative entropy, where we maximize over all the rho bars in the epsilon ball. And finally, we have the smoothed max information, where we're minimizing the max information over the epsilon ball. And lastly, the quantity that we're interested in is the partially smoothed max information. So this is the same as the previous definition, except that we additionally impose that this rho bar has the same marginal on the A subsystem. And we denote it with this extra dot up here. And the last quantity that we will see is the hypothesis testing relative entropy, where we want to distinguish rho and sigma using some two-outcome POVM, and we would like that our error in misidentifying rho as sigma is bounded by epsilon, so that's this condition, and then we would like to minimize the other error of misidentifying sigma as rho. Okay, so now that that's out of the way, let's start with quantum state splitting. So the task is the following. So Alice holds this state with registers A and A1, and the purification of the state rho is on the R register, which is inaccessible. And the goal of Alice is to send this A1 register to Bob. To do so, she and Bob share some pre-shared resource state, sigma KL, where Alice holds the K register and Bob holds the L register. Alice will apply this encoding operation to A, A1, and K, and then she obtains A and Q. The Q register gets sent to Bob through some noiseless channel. Then Bob applies a decoder on Q and L to obtain the register B, and hopefully the state that they're holding at the end of that, which we do as rho tilde ABR, is close in purified distance to rho ABR. We're interested in the cost of communication here, so we would like to minimize the log of the dimension of Q, which was the register that we sent across, over all encoders, decoders, and resource states. So let me say something about state splitting and why we're interested in it. So state splitting is a very nice primitive for many other tasks, and it's also a generalization of some tasks that we might be interested in. For example, if the A register is trivial, then this is just entanglement-assisted source coding. So that's one possibility. Another thing that state splitting is useful for is channel simulation. So the idea is if Alice and Bob want to simulate a quantum channel between them, what they would instead choose to do is Alice would just simulate the channel locally, which she can always do, and then state split the output. So this would be effectively simulating the channel. Finally, you can also have state merging, which is the reverse process where you would start with Bob holding the B register and trying to send it to Alice. It turns out that that has the same communication cost, so we can just choose to either study state splitting or state merging, and in this case, we'll just stick with state splitting. So let's now look at this quantity, Q star epsilon of rho AB, which is the communication cost. Now, our first result is that this communication cost is given in terms of the partially smoothed max information between the R and the B register of the state rho. So I will quickly say how we get this result. So for the achievability, the main technical tool that goes into it is the convex split lemma introduced by Anshu and collaborators. So the convex split lemma says the following. So suppose you have some set I from 1 to n, and you consider these Hilbert spaces, so B little I, where they're all isomorphic to each other, and little I runs from 1 to n, and B capital I is just the tensor product of all of them. Right? So now let us consider some state rho living on B little I R and also some sigma living on little bi. With these states, we can define the following extended state tau. So tau is a convex combination where you have rho on one of the i's, so let's say I equal to something. So you have rho on BIR and sigma on all the remaining BI's, right? And the convex combination is where we just vary little I from 1 to n. So for the convex split lemma says that if you have such a state, then the fidelity between tau, this extended state, and just the case where you have sigma on all the BI's, tensored with rho r, so that fidelity is close to 1 if n is large. And that's really the main tool behind the argument that gives you the achievability. In fact, the proof is kind of similar to what is in this reference, except that those authors leave it in terms of the smoothed max information, and we need it in terms of the partially smoothed max information. And for the converse, so we use this non-lockability property of the max information. So here we define omega, which is the encoded state, and tau, which is the state after the decoder has been applied. So tau, by definition, is epsilon close to rho ABR. And also notice that both the encoder and the decoder had identity operations on the R register. So tau R is actually equal to rho R. And that means that this first inequality holds. This is the partially smoothed max information, which is a minimization over all states which are epsilon close with the same marginal on R. Tau is one such state. So we have this inequality. The second inequality is just data processing. We just remove the decoder. And now we use the non-lockability property, which says that if you add a register to the max information, it increases by at most 2 times the log of the dimension of that register. So that's the third inequality. And the fourth inequality, again, is data processing, where we just remove the encoding operation. And here we're left with row tensor sigma here, and hence this Imax term is actually 0. So 2 log q is an upper bound to the partially smoothed max information. And that's the converse statement that we needed. Okay, so that was the one-shot communication cost of state splitting. And now we're interested in the case where we want to state split row AB tensor n, so n IID copies of it. So the first thing to look at is the asymptotic setting, so where we let n go to infinity first, and then ask that the error goes to 0. In that case, we just get 1/2 the mutual information between R and B of rho. And this makes intuitive sense because state splitting is essentially transferring correlations between the reference and the register that's being sent from Alice to Bob. So it makes sense that the result should be in terms of this mutual information. And now let's look at the case where n doesn't go to infinity, but instead we have finite number of n here. And in that case, we have to now decide how we want our error epsilon to behave. So there's 2 regimes. So the first one is the small deviation regime, where we just ask that the error be some constant, and the large deviation regime, where the error is exponentially decaying in n. So the reason why they get these names comes from channel coding. So in channel coding, let's say you have n copies of the channel, and you have the same question about communicating with some error epsilon, and you ask that epsilon is a constant, then the rate at which you communicate turns out to be the capacity minus theta n to the minus 1/2. So as n gets large, you get very close to the capacity, so there's a small deviation from the capacity. Similarly, if you ask that the error goes exponentially decaying in n, then the rate that you can achieve is a constant away from the capacity, and hence there's a large deviation from the capacity. So moderate deviation is essentially the setting where we want the best of both. So we want that the error goes to 0 in the asymptotic limit, but also that the rate approaches the capacity. So in our setting, we have state splitting. So we would like that the error goes to 0, but that the cost of communication approaches this 1/2 times the mutual information. So how do we achieve that? So to do that, let's first introduce a moderate sequence. So a moderate sequence is one where a sequence of numbers an, which goes to 0 as n goes to infinity, but n times an squared goes to infinity. So this is chosen so that, in particular, if you have n to the alpha for some alpha between minus 1/2 and 0, then that's a moderate sequence. So the error that we're going to require is going to be en to be epsilon n to be e to the minus n an squared. And you can see that because this condition is true, the error indeed goes to 0 in the asymptotic limit. And with this, we can now look at the main result, which is the communication cost of epsilon n error state splitting of this state, rho AB tensor n. And it turns out that the cost is 1/2 times the mutual information plus these terms, where this is the relative entropy variance. And notice that you have this an here and little o of an here, and both of those will go to 0. So indeed, as n goes to in the asymptotic limit, we will indeed have that the cost goes to this mutual information term as we desired. Finally, I will say something about the proof of this theorem. So I won't have time to go into the full proof. So instead, we'll just look at the main ingredients that go into it. So for the achievability, what we need is a bound between the partially smoothed max information and the smoothed max information, and that's given in this reference here. This smoothed max information is essentially a max relative entropy, and we can bound the max relative entropy with a hypothesis testing relative entropy as shown here. And finally, for the hypothesis testing relative entropy, in the moderate deviation regime, so where epsilon is e to the minus n squared, and you have IID states here, one has this expansion. So these are the main steps that let us go from a partially smoothed max information to an expansion of this form, which is what you saw on the previous slide. And finally, for the converse, the ingredients that we need are firstly a tighter triangle inequality for the purified distance. So this triangle inequality says that for some states rho, sigma, and tau, where the sum of the squares of the purified distances between rho and sigma and rho and tau is smaller than 1, then we have that the purified distance between rho and tau is bounded as shown here. And these are fidelities which are smaller than or equal to 1, hence this is a tighter version of the triangle inequality. Using this, one can actually bound the smoothed min relative entropy with the hypothesis testing relative entropy. as shown here. So this is kind of the key step, because then once again, for the hypothesis testing relative entropy in the moderate deviation regime, for IID states, one has an expansion as shown here. So these are the steps that go into the converse proof. Finally, I will say something about the questions that are still open. So firstly, state splitting in the large error regime doesn't exactly work. So in all the things I've shown you so far, the error epsilon has been e to the minus n an squared, which goes to 0, of course, as n is large. But we would also like to look at 1 minus e to the minus n an squared. And in that case, the converse proof kind of works, as I've shown you, but the achievability proof doesn't, so it needs some new techniques. We also have a gap in the second order analysis. So this is the small deviations regime where the error is fixed. So there's a gap between the achievability and converse statements, and one that we hope to close at some point. And finally, there's also the error exponent analysis. So this is the large deviation regime for state splitting that we could look at. Thank you for your time, and here are the references.
Okay. Thank you for your talk. So I see that there are questions, but since we are running out of time, I would like to direct people to the Slack channel to post these questions. Thank you very much for your talk.